Okay, so any questions before we begin? Now we are kind of losing 3 hours tomorrow, so we are on a tight schedule. So I will be kind of skipping some of the material. I will be just picking up certain subjects which I think are important from this chapter, the Maxwell's equations, and also from the next one. So this today and next week, it will be kind of a mixture. You won't have any pre-reports for next week. You will have a homework nevertheless. And yeah, any questions before we begin?
Can we extend the class today? Can we extend?
Unfortunately, no. It is somebody else's, not mine. Other questions related with physics? Now, we will come to that today. We will be discussing that today. Now, let's first summarize with equations what we had learned since the beginning of the semester. We have the Gauss law for electricity, which basically states that if you take the electric field and sum over all the electric field over a closed surface, then we know that this is equal to the enclosed charge divided by epsilon 0. Well, this is basically a statement that the electric field can start from closed charge, from point charges, or they can end at point charges. So in a sense, the electric monopole exists. There is a similar law for the magnetic field, B dot ds, but this is basically 0. Because we know that the magnetic field line, at least experimentally, we know that all the magnetic fields that we could test, they all form closed loops. So they never end at a point, or they never start from a point. So magnetic monopoles do not exist. They are not magnetic monopoles. You cannot have magnetic field lines leaving from the black holes. Okay, you see, just imagine this. You have a black hole. First of all, you have to create the magnetic field line. Then you make it approach to the black hole. What happens is, even black holes, they are not magnetic monopoles.
How can the electric field go this way and it's not going out so?
The electric field?
No, magnetic field. Magnetic field is coming the way.
Well, you see, the properties of the black holes can be charged. They can have electric charge. So electric field lines can start from a black hole or end in a black hole. And they can also move. So we will see that if we have moving charges, then we create magnetic fields. But those magnetic field lines do not start on the charge.
Can the magnetic field come out to black hole?
You see, magnetic field lines are not physical objects. That's also another thing you have to keep in mind.
Can you draw a bar magnet, a simple bar magnet?
Yes, I can.
Now, the follow-up question is, it's 3 parts. The second question is, can you draw a Gaussian surface that covers only the north part?
Sure.
Now the slightly challenging question is, technically wouldn't the magnetic field just leave the circle and not enter back? Because it sort of curves to go to the south part, right? So wouldn't we say mathematically that's a magnetic monopole? But that's cheating. You only go
No,
to
that's
the south part.
that's not cheating. This is what a magnet does. I mean, you see, a magnet just acts like a solenoid. You can, in fact, define the current density on the surface of the magnet such that it will create exactly the same magnetic field. So it just acts like a solenoid.
Thank you.
So, in fact, this is why we cannot, even when you break the magnet, you don't get monopoles. You get still dipoles, because what you are actually doing is you are breaking, if you just break it over here, so the magnetic field lines are just leaving from this surface and entering this end of the other magnet. So you have these two dipoles.
What you do is for the dimensional equivalent. You say E dot ds equals Q into sigma E dot dp.
Can you repeat it?
Isn't it E dot dp?
Oh, ds is dA. ds is infinitesimal surface element. Well, most of the time the convention is either to use A meaning area or S meaning surface. Now, you see, this is experimentally. We have never observed a magnetic monopole yet. That doesn't mean we are not looking for it. Some theories are predicting that they should exist. And those theories have some nice properties, so we will be happy if there is a magnetic monopole. At least it will also explain us why the electric charge always comes in the multiple of some unit. You get the electron charge, twice the electron charge, minus 5 times the electron charge, but we never get the 0.3148 times the electron charge. Never. We don't know why. But if there's a magnetic monopole somewhere in the universe, then we have an answer, which you will learn when you learn quantum mechanics.
So you just said that the bar magnet actually acts as a solenoid. So does that mean that it has charges that's moving like this?
Not really. What's actually happening is we have the, I mean, a bar magnet, you can just imagine it as very small magnetic dipoles. Very small. So we define the magnetic dipoles as just currents running in circle. So just imagine this one. You have a magnetic dipole, a very small one over here. Well, let me a bit exaggerate it. A very small one, another small one, another small one, another small one, another small one. All of them are going in this direction. So the charge, I mean, there isn't any charge that is moving around it, but the charges are kind of making a small circular motion at every point. Now, if you consider the total current here, there is a current going down around this loop. There is a current going up around the next dipole. On the average, they just cancel. They cancel here, they cancel here, they cancel here, they cancel here. They cancel everywhere inside. Only there's a current on the outside. There's a current over here, a current over here, a current over here. So this system is effectively, you can treat it as this system. They will behave identically in terms of their magnetic properties. In this sense, there is a current running on the surface of the magnet.
Well, hang on. This is kind of cheating because because it's just one electron moving, doing this. So you said the current can at one point cancel the current at the other point. But,
On the average.
on the average. But still, when the electron is there, the other one is there, there's no current here.
On the average. I mean, you see, if something is oscillating, let's say at 1 billion hertz, do you have a device to measure it? No. If you don't have a device, what you will be measuring will be the average value. So on the average, the magnet just behaves like a solenoid, on the average.
So if we have enough time and enough distance to can you create monopole in the time that's so?
Well, you see what you are, is this what you are saying? Just take a magnet that is huge.
Yeah.
Well, every end will behave like a monopole. I agree. Each end, if you don't go inside, of course. I mean, you see, if you would treat this end as a monopole, if it is very long, you are right, just like an ordinary electric monopole, the magnetic field lines will just go radially out, except on this region. And that, except on this region, makes the whole difference.
Can I ask one more thing? We always draw magnetic magnets, bar magnets, as this long, thin thing. But can't they be kind of more flattened? Like the end will be very wide.
Well, I'm sure you have also seen these magnets.
Yes.
Just go to Bauhaus and you will be able to buy magnets of this shape.
So, well, hang on. In the,
I mean, you can build magnets of any shape that you like.
in the horseshoe magnet, the North Pole is the what?
Well, of course, if it is a properly made horseshoe, I mean, you can also make horseshoe magnets where this will be the north, this will be the south, there will be another north over here, another south over here, even some south over here, and the north over there.
Very good.
Depends on how you prepare it.
So how do we make magnets like that?
Well, iron, if you just look at it at very small sizes, it's a magnet already. It's a natural magnet. It's just the problem is, just like over here, various poles, the various dipoles in an iron are just not aligned. So they don't add up to give a large magnetic field. They just add up to give a small magnetic field or zero. Not something that you can measure. So what you do is you melt them, put it in a magnetic field, so that since they are already melted, they can just rotate around, put it in a magnetic field, and slowly cool them. So all the magnetic dipoles will be aligned. So you will get a permanent magnet. Okay, Biosawar, we didn't come there yet. We will come there in a moment. So let's first stick with these two. Do you agree with these two? Any questions on these two?
So you can teleport things.
Who?
Teleport. I mean, we know.
Well, I don't know how to teleport things using magnetic fields or electromagnets.
Teleport that magnet while the.
You see, what is teleporting? First define me that. And then I can answer your question based on your definition of teleporting or the technique that you use for teleporting.
I want to be information.
Okay.
Information transfer.
Okay, that is something else. Information doesn't have a magnetic field, though.
Disintegration and reintegration. Disintegration and reintegration.
Of what? In the sense of the Star Trek?
Well, something like that.
How does it work? I mean, he will be asking me a question about what happens when you teleport, but without knowing what is teleporting is, how can I answer that question?
If I tell you, I'll probably get a Nobel Prize myself.
Sure. Don't share it with anyone. Okay, let's continue. Then we had this equation, E dot ds. Well, you see these two also share one more property. There is no time dependence over there. But they are still valid whether we have a time-dependent field or time-independent field. These two laws are still valid in electrodynamics also. Now let's see the equations that tell us how the time dependence comes into the game, how the time dependence affects the electric and magnetic fields. So we get the electric field integrated over a closed loop. Then we know that this is minus d phi b by dt, or let's also write this magnetic flux explicitly, d by dt of b dot dA. Now, there's one thing we have to be careful about. Here, we have we are calculating the flux over an open area. This is not a closed area. Let's just call that that surface S. Now the boundary of that surface is a closed loop. Just imagine any surface. For example, this is a surface. The boundary, the edge, it just forms a closed loop. And the integral over here, that this closed loop, is over the boundary of this surface. I will be using this notation for that. ds is the edge of the surface S, which is a closed loop. And this law basically told us that if you have a changing magnetic field, then there's an electric field created. So we had the first law, the Gauss law for electricity, which says that if we have charges somewhere, we do create electric fields. But now this law also tells us that there is another source of electric field. If there is a changing magnetic field, then that also creates an electric field. And then finally, we had the magnetic fields. If we integrate the magnetic field over a closed loop, this was equal to mu0 times I. This is what we know up to this point. And Biot-Savart law is, you can say it's a consequence of this one, or this is a consequence of the Biot-Savart law, etc. Now your question.
My question is, you apply, you explain the use of Biot-Savart and the Ampere's law in finding the magnetic field a wire. My question is that in using Ampere's law, irrespective of the length of the wire, it is the same wire.
The same?
Irrespective of the length of the wires, it will give the same value, that is P0 I plus pi. But for the Biot-Savart, if the wire is finite, it will give that value.
No. You see, your first question is this one. We have the Biot-Savart law, so which tells us the magnetic field created by a very small segment of a wire of length dl. This is the magnetic field created, right? And if we have a finite length wire, then the magnetic field will be different if we have an infinite length wire. So, but on the other hand, if we use this one, the Ampere law, then this gives us B is equal to mu0 over 2 pi r times I, let's say the magnitude. Now the question is, where did we use the fact that the wire was infinite or finite? Did we use it at all? Did we use it or not? In this one, we did. How we used it, you see, how did we evaluate this integral? I mean, you see, when we were using the Ampere's law, we first said that B dot dl is equal to 2 pi r times B. Now, here we already used it. How did we use it? What is the magnetic direction? We have to determine, if we want to use the Ampere's law, we have to determine the direction of the magnetic field first. What is the direction of the magnetic field? What does it depend on? If it is an infinite wire, then the magnetic field doesn't depend on whether we are over here or we are over there. It is independent of that. That is one thing we use. Now, if it is finite, the magnetic field here will be different than the magnetic field here. If it is infinite, the magnetic field here will be the same as the magnetic field over here. This is one place where we used it. Where else did we use it? Well, even if it is finite, it does have this circular symmetry. You're right. Almost. there is still one problem. You see, we could have said that this is okay, this is equal to BR. It might also depend on some value of Z. I'm just imagining such a circle. Well, in that case, the magnetic field doesn't have to be radially out. It can have some vertical component also, if it is finite. So then this would just tell me the radial component. So the radial component of the magnetic field, no, that's not the radial component, sorry. It is the tangential component, the circular component. Let's just put this one T. But it can also have a Z component. And using this law, using Ampere's law, we cannot determine the Z component. That is one problem. If we take it finite or infinite, it will be different. Now, there's another problem, though, which is the point that we will be discussing now. You see, if you have a finite wire, a wire of finite length, which is carrying some current I, a constant current I, this is not a magnetostatic problem, though. Why is it not magnetostatic? Current is not changing in time. But there is something that is changing in time. So what does the current do? What does the current do to charges? It just moves it. It moves it around. So we have, let's say, positive charges over here that are moving up. So what do they do here? They will accumulate. So this pool will be charged positively, and the charge will change in time. Now the question is, how does the Ampere's law, is the Ampere's law still valid in this case, or do we need to modify it? Now that is the question that we will be addressing now.
Well, my case is, I don't have to do your, in this case you separated the, I'm talking about, I'm looking at it, then a loop, I mean complete loop. And I take just one side, that's which.
You mean this? You mean this loop? A current carrying loop. Okay.
I mean, let's say square root. A square root. Okay, I just look at the other end. That is required. And it's fine.
Now, this is even more complicated. You see, this side is finite, fine. So you imagine such a loop. But now the magnetic field at this point and the magnetic field at this point, they don't need to be the same. Because this point is at a different distance to these wires than this point. And at every point, there will be contributions from all these four wires. So since the B will not be uniform around this loop, B.dl over this loop will not be equal to 2 pi r times B. Because B here will be different than B here, will be different than B here. I mean, there's no guesswork. It's just not equal to. That's it. We cannot do much.
So are you saying that by superposition, I can, if I use the, I can apply the same amplitude for all the four wires, then superimpose all the items. Is that what you're saying? I find the magnitude of each wire using amplitude and superimpose everything. Is that what you're saying?
That is one thing you can do. You can just take this wire, assume that it is carrying a uniform current, but in that case, then solve for the magnetic field of that wire only. But in that case, that wire is this one. It is accumulating charges Then you can imagine the other wire over here. Calculate the magnetic field created by that wire. Well, this point will be neutral because it's plus Q from here, minus Q from the other one, so it will be neutral in the superposition. So if you just take just one of them and try to apply the Ampere's law, you hit this problem.
But infinite wire, what exactly does this accumulated charge do?
Infinite wire.
No, finite.
In the finite one, we'll see in a moment. But let's first take a simpler example to see the problem. First, let's specify the problem, what's the problem, and then see how we can solve the problem. How the charges are accumulated? Okay. How? Well, you see, you are carrying a current, right? Current is just moving charges. So you are adding positive charges at this point. There's no place for them to go. Where do they go after this point? If you imagine that they are moving up, so then this current is continuing. It's not finite. Which ones? Okay, we have this infinite wire. So the charges are all moving up to infinity. They are not accumulating anywhere. There is no accumulation of charges. But here we are saying that we have a finite wire. The charges cannot move. Well, let's first define what we mean a wire. A wire is just a very thin, a current. When we say a current carrying wire, the material is not that important for us. What counts for us is that there in a very narrow region, almost a line segment, there are moving charges in that line segment only. Then the problem is when they reach the end of that line segment, what happens to those charges? In the infinite wire, there is no end of the segment. So the charges can just keep moving up to infinity. In this one, what happens to them? If you want to solve the problem, you have to add it also to your problem. Well, because you see, when you are calculating this one, what you do, you just divide the circle into very small segments, calculate the B at each one of those segments, and then sum them up. But you see, the magnetic field here will be different than the magnetic field here. So B, the magnitude of B is not constant. If it is not constant, if it depends on which point you are on the ring, you cannot take it out of the constant. So this, equating this one to this one, is equivalent to taking the constant magnitude of the magnetic field out of the integral. If it is not constant, you cannot take it out of the integral.
So one thing on what you said about the accumulated charges.
No question on accumulated charges. We will be discussing them in a moment. Hopefully it will be more clear. No. Okay. No question on accumulated charges. No. What they are asking is, just imagine, hypothetically, you create a current on a wire, on a finite wire. What will be the magnetic field created? Now let me continue. Let's imagine an infinite wire, almost infinite wire. Well, we know that B dot dl, which is carrying a current I, this is equal to mu 0 I. Any questions on this one, the infinite wire? So let's just take this loop over here. This is my L. There I have a loop. Well, the wire need not be infinite, but very long. And let's say I'm talking about a wire that starts from here, and it's straight, goes to the Andromeda galaxy in one direction, and to some other galaxy in the other direction. And it is carrying a current I. And somebody in the Andromeda galaxy decides that he wants to put a capacitor over here. But we kind of make sure that the current is always I. So the magnetic field here, will it change due to this capacitor in the Andromeda galaxy? It shouldn't change. I mean, we won't be affected by what happens in the Andromeda galaxy. Okay, so that's fine. The B is the same. B dot dl will be equal to this one. Now, what is the current? Let's also define it more properly. If you remember how we define the current, we just assumed an area and counted the charges that passes through that area. So this is equal to mu0 times J, which is the current density, times dA. This is over a surface whose H is my loop. So I just assume an area in my loop, sum all the charges that is going through that area, and then the integral of the magnetic field around my loop is equal to the total charge that passes through my surface. Any questions on this one? Well, what is the surface? Okay, so your friend said that let's just imagine this as our surface. No problem, right? Well, what if we imagine this as our surface? Will it change anything? Will it change anything if we imagine such a surface? Nothing will change. There is still the same current is passing through this surface. What about this one? This is S3. Now we have a problem. On the one hand, the existence of this capacitor doesn't change the magnetic field. The magnetic field is not affected by the capacitor. So B dot dl doesn't change. On the other hand, on the right-hand side, I have some quantity which changes depending on what kind of a surface I choose. So this is something we have to solve now. Any ideas? Now, you see, the problem was we had this law, the Ampere's law, which is valid in magnetostatics. We have tested it, etc., so there's no problem with this law in magnetostatics. Now we have a dynamical system. Something is changing. So if we add something that contains, let's say, the derivative of some quantity over here, of course, we are not spoiling the law in magnetostatics, because in statics the time derivative will be 0. But we might be saving this, let's say, contradiction over here. What is changing in time in this problem? The charge over here is changing. So here we have a charge. Well, my surface doesn't feel the charge, but my surface feels the electric field. So there is an electric field over here between the plates, almost uniform, which is changing in time. So for such a surface, I have to add something over here that contains the change in time of this electric field over here to save this law. If I add a suitable term, now the suitable meaning that if I choose such a term, it should be 0. Such a surface, the additional term should be 0. If I choose this surface, the additional term is 0. If I choose this surface, then I is 0, but the additional term should be equal to I. So that for every surface, the sum of those terms will be the same.
If we go over to the other side of the capacitor and take this surface 4, it's going to be the exact same thing.
Sure. So we can just take this one, but for this surface, there is no problem because there is the total current passing through S4 is just I. So let's see how we can relate the change in the electric field here to the current. Now, what is the electric field in the capacitor? Sigma over epsilon 0. What is sigma? Q over A times epsilon 0. So Q is A times E times epsilon 0. What is I? I is dq by dt. This is equal to epsilon 0 times d by dt of A times E. What is A times E? The electric flux passing through this surface. This is equal to epsilon 0 d phi E by dt. So this is my I. I had this law. But then we had regions, we could imagine surfaces in which I was 0, but nevertheless this quantity is non-zero for those surfaces. So we can just add them.
I cannot understand why that.
Let's see what we are resolving if we add them. Let me just draw another one over here, or just copy this one.
This adding field creates a current, and this adding current, right?
You see, B dot dl has a given value, independent of what kind of surface I imagine over here. B dot dl only depends on the magnetic field on this ring, on this loop. So B has a given value, fixed value, independent of how I choose this surface. dl has a given value on this loop. So this integral has a fixed value. Whether I choose this surface, this integral has one value. Whether I choose this other surface, the integral has exactly the same value. Now, for these two surfaces, that value is equal to mu0 times I. For this other surface also, the integral should be equal to mu0 I. But now I cannot identify I as the total current running through my surface, because there is no current running through my surface. But there is something else that runs through my surface, the flux over here. And I can relate the flux over here to the current running through my surface. So this is, I have only mu0 I for S1 or S2, mu0 epsilon 0 d phi E by dt. This is for surface 3. But you see, I don't want to look at a surface, and my law shouldn't be dependent on what kind of a surface I have. For surface 3, I is 0. So if I add I over here, I'm just adding 0. For surface 1 or 2, there's no electric field. Since there's no electric field, the electric flux is 0. So if I add this term over here, I'm just adding 0 for these two surfaces.
Okay, but for
This one.
there's also a capacitor, but
You see, the electric field is confined in the place between the capacitor. So there's no electric field on S4. Now, there's another interesting surface, though. Let's just imagine such a surface. Or even this one. Now, is the right-hand side the same quantity? Is this is equal to mu0 j dot dA plus mu0 epsilon 0 d by dt of E dot dA, the integral of the electric field over this surface. Well, let's see. If I calculate this one, here I have a I. There is a current, the total current running through my surface at this point is I. I already get a contribution I from here. So this term is already I. Well, you see, this one has to be equal to mu0 I. Because I can just imagine a small surface over here. So this loop integral value is mu0 I. Now let's look at this other surface. From here I get a mu0 I already. Then I have some additional flux over here, which is time dependent. Let's say partial. Not all of the, my surface doesn't go over all the area of the capacitor, but just goes over partially. So what cancels this one? There should be something that's canceling this one, right? I already have the mu0 I, and it should be equal to the b dot dl integral. What is canceling this one?
It crosses the plate.
Exactly. It crosses the plates. When the charges are reaching the plates, they have to be spreading out. That means some charges will be moving through the surface. Well, this one was going out of the surface. The charges here are going into the surface. That is what cancels this one. There is a current on the plates. And these two terms should cancel each other exactly. So kind of whatever surface we imagine, if we write our law in, let's say this is called the Faraday-Maxwell's law. Now there's a Faraday-Maxwell's law. And if we just add these two terms, if you write the Faraday-Maxwell's law in this form, this law is valid independent of which surface you can imagine to define the right-hand side. So it will be always valid. And it should be. The surface is our choice. We are just inventing surfaces. So the physics, the magnetic field shouldn't depend on what we are inventing. So this kind of completes the Maxwell's equation. So these four laws, let me just rewrite them again. These four laws are enough to describe all the electromagnetic properties. Let me just add one more. The Lorentz force. So basically, the Lorentz force will determine how the particles are accelerating around you. And Due to their motion, the motion of the charges, you will be creating currents, and the charges will be changing. You will be creating electric and magnetic fields, which will be influencing how the charges are moving. So these 5 equations are enough to describe all the electromagnetic phenomena that you can imagine, including questions like, why is this orange? Now, it's enough to know these equations. Why is glass transparent? Why does it allow visible light to pass through? Of course, you have to add some. Well, in fact, with this one, that's enough. All the answers are in these 5 equations.
Hocam şu üstteki eşitlikte
This one.
yok. En üstündeydi. İkinci terim şu en alttaki işlemdeki ikinci terim. Evet. O partial alana bağlı.
In this surface, there is a electric flux, which is changing in time.
Yani biz o surface'i değiştirerek şu ikinci terimi büyütebiliriz.
Sure, I mean, you can just assume a surface like over here.
Ya o zaman bu üçüncü terim de mi o şeye bağlı?
It also depends on the surface. I mean, these are not just lines, they are plates. So since they are 3-dimensional objects, if you move the surface inside, it will be intersecting your plate at a larger area. This will also grow, not just this one. Both of them will grow. They should cancel each other exactly.
A current running a wire which has a capacitor. So in normal circumstances, with a constant EMF, the I should have changed. But
It's not a constant EMF.
the EMF isn't constant.
You already have the answer. Let's give a break, and then we will continue after the break.